One-dimensional force problems. What do I mean by one-dimensional? The most that we're going to be doing is moving left and right or up and down, but we're not going to be moving up and down and left and right at the same time. We'll get to that. What are some classic one-dimensional force problems? The elevator or apparent weight problem, standing on a scale in an elevator. Air resistance, friction, we'll do a separate lesson on friction, and the many body problem, we'll do a separate lesson on more than one mass. We introduced this concept to you last year of the normal force. What's the normal force? It's the contact force between the floor or a surface and the object sitting on that surface. You can feel the normal force if all of you lift your legs off of the ground right now, hold them midair, and now you'll be much more aware of the chair pushing up on you, exerting a normal force on your body. Because of course, what are the forces acting on you? Get the obvious one. Gravity is pulling you down. Are you accelerating down? No. That means the net force must be zero. The forces are balanced. And so we give that name, we call that force a normal force. By the way, normal force doesn't exist. It's not a real force. All of you right now, take your non-writing hand or your writing hand, push down hard on the table. Can you feel the table? Push hard. You're touching the table? No, none of you are. None of you have ever touched anything in your life. Okay? What's actually happening on the microscopic level is the table has a bunch of electrons in the outer edge of its atoms and molecules. Your hands, the skin, has a bunch of electrons in the outer edge of its molecules, and like charges repel. As you get really close to the atoms in the table are repelling the atoms in your skin, and your nervous system feels that as pressure and tells your brain, oh, I'm touching it, but you have never ever come close enough to actually have the atoms in your skin come in physical contact with anything. With anything. Everything that you think of as pressure and as touch, it's all actually comes down to, there's only four fundamental forces. There's gravity, there's the weak nuclear force, there's the strong nuclear force. Those explain radioactivity and what goes on in the nucleus. But then the fourth one is electromagnetism. And that's really the force that everything comes down to, technically. Not on your test, but just kind of for nerd trivia. However, the normal force is also the value that something would read if you were standing on it. Who else remembers where the normal force would show up? Yeah? A bathroom scale. When you stand on a bathroom scale, Alexis, when you stand on a bathroom scale, Nick, a scale does not measure mass. It measures the normal force, and I'll prove it to you. So I wrote here, a normal force is also the value that a scale would read. Scales don't read weight. They read the normal force. And that's why a nickname or another expression for normal force is your apparent weight. Your true weight is mg. But that's not what most of you feel. Most of you feel your apparent weight. What's your apparent weight? How hard the floor pushes up on your feet. That's why if you're giving somebody a piggyback, you feel heavier because the floor is having to push up harder on your feet. Your mass hasn't changed. There's an extra mass in the free body diagram. Your weight hasn't changed, but your apparent weight has changed. All of you right now feel a normal force that equals mg, the force of gravity. All an amusement park ride does is it messes around with the normal force. I think I showed this video last year, but we'll watch it again. So what does a scale measure? A scale measures normal force, not mass, not weight. It measures normal force. So let's imagine you're standing on a scale in an elevator. A person with mass little m and weight big W is in an elevator standing on a bathroom scale. But instead of having the scale display kilograms, let's pretend it reads newtons instead of kilograms. By the way, all the scale does to display kilograms is it takes the normal force and divides it by 9.8. And that's what it's calibrated for. If the elevator starts at rest and accelerates up, what will the scale read? W more than W or less than W? Once again, we're going to vote. Once again, how high we hold our hand up is how sure we are of the answer. So if a person is if you are standing on a scale, a bathroom scale, and your mass is m and your weight is big W, if the elevator starts accelerating up, will the scale read W, more than W, or less than W? Who says, Mr. Dewitt, this is easy. You're standing on a scale. It's going to read W. That's what a scale reads, W. No one. Huh. More than. Amazingly, even Adam voted for more than. He went with the crowd for a change. So there was a none. Convince me. Convince me. What might this be a good job for? A free body diagram, you say. Let's represent this person with a dot. What are the forces acting on this person? Get the obvious one. Now, I notice they want me to call weight instead of mg. They want me to call it W, so I'm not a fan of that because to me W is west, but I'll follow the question's notation. What else? Which way is this person accelerating? So which way must there be a bigger arrow pointing? What force is that? It is the normal force. It's the floor pushing up on their feet. Who's winning? The normal force minus weight equals ma. So I guess the normal force is going to be the weight plus ma if I get the normal force by itself. A scale reads normal force. So I probably mentioned that. Scale reads Fn. Well, since the normal force is the weight plus something, I think the normal force has to be bigger because you're adding something to the W. Scale reads N. Fn is greater than W. There's a proof. Example 2 said write a net force equation. Hello, right there. Already did. What if we were, or did I ask that as a part follow-up? Maybe I did. No. What if we were accelerating down? What would you feel? Lighter. Lighter. Okay. Example 3. A student stands on a kilogram scale, so a kilogram scale reads the normal force but divide by 9.8. If the elevator accelerates down at 2.25, find the normal force, find the scale reading. Any thoughts on how I might want to start this one out? A free body diagram, you say. I'm going to do mine in the margin over here. What are the forces acting on this person? Get the obvious one. Which way are we accelerating according to this question? Down? So which way must there be a larger force pointing? Is there a force pointing up? How do I know? How do I know? If we were in free fall, what would A be as a number exactly? 9.8. Is it 9.8? So there must be a force up, but since we're accelerating down, I know it's smaller, and that, again, is the floor pushing up on my feet. It's the normal force. Who's winning? mg minus. Who's the loser? What does winner minus loser always equal? What's part A asking me to find? What's right in front of the Fn that I don't like? This is where I introduced something that we nicknamed the swappy dance last year, where we said, you know what, Allie, I can plus that to that side and simultaneously minus that to that side. Why not? Because that'll get the Fn by itself. And I'll end up with mg minus ma equals Fn. M 35. G. Am I going to put in a negative 9.8? I took care of that with my winner minus loser. In fact, I'm letting down be positive this time because it makes the math easier. Minus M 35, A 2.25, and I get 264.25. I'll call it 264 newtons. Is that right? Now, of course, a real bathroom scale, a standard bathroom scale, doesn't read newtons. What does it read? Kilograms. So part B says, what's the scale reading? I'm going to do part B right up here because I got room. How would I change newtons into kilograms? Yeah, it's going to be 264 divided by 9.8, although I'm going to use my answer button, divided by 9.8. And I get 27.0 if I go to 3 sig figs. So 35 kilograms originally, 27 kilograms. They feel lighter. Has their mass changed? Nope. What's changed? Their apparent weight, the normal force, the weight that you feel. Example 4, what's the normal force for the following object? You'll notice on your formula sheet there is no equation that says Fn equals and some way to calculate it. We will always get it from a free body diagram. And on that note, this is a job for a free body diagram. What are the forces acting on this 5 kilogram mass? Get the obvious one. What else? There's also a 15 pointing down. See it? What else? And then I think last year I would have said something like, is this mass sinking into the ground like quicksand? Is this mass flying into you like Superman? So that means in the vertical direction, the forces must be balanced. This year I'm probably just going to say, hey, what's the vertical net force? 0. So there must be an arrow pointing up, bigger, smaller, or the same size as mg? Bigger. How do you figure? Oh, okay. So it's going to be like that big. There's the normal force. In fact, if I was being really, really fussy, Max, I would draw this arrow the same length as those two arrows combined, if I really wanted to try and be roughly to scale, because they're equal. Give me an equation, Max. What does the normal force equal? Are we sinking to the ground like quicksand? Are we flying into Superman? What's our acceleration? So you could go, don't write this down. Who's winning? Normal force. Who's losing? 2 losers. mg and 15, and that equals 0 because we're not accelerating. But a better way would be to say it's a tie, which means everything up has to equal everything. The normal force up has to equal the mg and the 15 down. That's our equation, vertically. And now I can plug and chug. It's going to, I can do that in my head. 5 times 9.8, I'm pretty sure is 49, plus 15 is 59. 64, double check me. In example 5 here, I'm giving you the net force at the bottom. We wanted to fill in the missing forces and decide whether it's accelerating. Let's decide whether it's accelerating first. We'll just circle yes or no, then we'll fill in the missing forces. Object, the first one, accelerating or not? How do you know? Net force is 0. Now, what does that mean? It's either at rest or it's moving at a constant velocity. I don't know which. What about the second one? Accelerating, yes or no? Sorry, I circled yes. I should have circled no. Here I should circle yes. That's my bad. What about the third one? Got to be accelerating. What about the fourth one? Got to be accelerating. Now let's go fill in the missing forces. So how big must force A be exactly? Sorry? Got to be 50. How big must force B be? Has to be. Ooh, how big must force C be? I'll give you a hint. Not 900. I think it's got to be 1100 newtons, and that gives you your net force of 900 up. How big must force D be? Sorry? What about E? Since there's no vertical acceleration, I have to assume that in the vertical direction, the net force is 0. The forces are balanced. Ooh, first of all, how big must force G be? Sorry? 50? How big must force F be compared to force H? So I'm going to say F has to equal H, and H has to equal F. Has to. So for elevator questions, do a free body diagram. Gravity's pulling the object down, mg. There's a normal force pushing it up, Fn. Who's winning? Which way are we accelerating? Who's losing? The other direction, equals ma. And I'll either give you the normal force and say find the acceleration, I'll give you the acceleration and say find the normal force, or I'll give you both the acceleration and the normal force and say find m, the mass. But we'll look at that later. We haven't got to that yet. Another force that we looked at last year is air resistance. Air resistance is a really, really tricky force. If you've ever held your hand out of the window when your car is moving, you may notice that as you go faster, what happens to the force you feel against your hand? It goes up. And you may notice, though, that you can reduce it by turning your hand. In fact, you may have done I'm going to pretend I'm an airplane and I'm going to fly. And so air resistance, it depends on your cross-sectional area. It depends on how fast you're moving. It also depends, believe it or not, on the density of the air. So at different altitudes, air resistance, as you get higher, gets smaller. We don't have the tools to deal with that yet, but we can kind of look at it in snapshots at certain times. The key idea is that air resistance has direction opposite to motion. So now let's turn the page. I think I might have done this last year, but it's a good repeat exercise. It says draw free body diagrams for each of the following. What we're going to do is we're going to throw a ball. In situation A, the ball is still in my hand. In situation B, it's left my hand, but it's on the way up right there. And in situation C, it's on the way back down to my hand. Right there. Okay? What are the forces on the ball when it's in my hand? Get the obvious one. We can call it a normal force if you treat my hand like a circuit, like a surface. You could call it F throw if you wanted to. Let's call it F throw because my hand isn't really a flat surface. It's kind of curvy and bumpy. We haven't looked yet at slanty surfaces, so I'm going to call it F throw. Is F throw bigger, smaller, or the same size as mg? Why must it be bigger? Ready? I'll show you an example where there's a vertical force that's smaller. Watch, 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 watch. I was applying an upwards force, but what did you notice? The ball did not leave my hand. For it to leave my hand, I've got to apply a force bigger than mg. So let's go F throw. I don't know. And we'll ignore air resistance while it's in my hand. But once it leaves my hand, part B, it's on the way up. Now let's include air resistance. What are the forces acting on it? Get the obvious one. Which way? What else? Air resistance. Which way? Down. Oh, because it's on the way up. Air resistance acts in the opposite direction of motion. How would I put 2 downs? I might just move the other arrow over a little bit, like that. I think air resistance in this case is smaller than gravity, but I need some numbers to be sure. C, on the way down. What are the forces acting on it? Get the obvious one. Yep. What else? Pointing up, bigger, smaller, the same size as mg. I think so. Now, the question would actually need to tell you something like, it's still accelerating. Well, then I know it's smaller. Can air resistance ever be the same size as mg? Oh, that's what terminal velocity is. In fact, I have experienced air resistance the same size as mg. Can air resistance ever be bigger than mg? Yeah? How? Right when I opened my parachute, which way was I moving? Down. But I slowed down, so which way was I accelerating? So which way must there be a larger force pointing? Yeah, air resistance was bigger than gravity. Otherwise, I wouldn't be here talking to you. In example 6b, in this middle one right here, this one, how can the ball be going up when all the forces are pointing down? What's that mean? That's like saying cos physics. Convince me. But doesn't the fact that I'm accelerating down, doesn't that mean I have to be traveling down? Sorry? Slowing down, and this is the key. We need to realize velocity and acceleration are two different things, and they don't have to be in the same direction. Eventually, if you accelerate long enough, your velocity and your acceleration will match direction. Because in this case, it's slowing down, comes to a stop, and then starts to point down and move down. So, explain your answer. I would say something like this. A is down, but V is still up. Acceleration does not tell me which way we're moving. It only tells me, Newton's laws tell me which way we're accelerating. For me to know which way we're actually moving, I need more information from the question. So yeah, you can totally be moving up with all the forces pointing down. Totally. Example 8 says, for 6c, write a net force equation. Well, who's winning? Who's losing? And that would equal MA. That's about the limit of what we're going to do with air resistance. I'll have to give you the information at a specific spot as though I'd taken a snapshot of the situation. 90-kilogram parachutist free falls for a time and then opens the parachute. The parachutist slows down at a rate of 1.5 meters per second squared. A says, compare the forces that act on the system. That's physics speak or physics code for draw a free body diagram. So here's the parachutist. What are the forces acting on this parachutist? Get the obvious one. Which way? What else? Air resistance, which way? Bigger, smaller, or the same size as mg? Bigger. Smaller. Convince me. Oh, we're slowing down, which means we're accelerating up. Means the bigger force has to be pointing up. Yep. So I've done my free body diagram. I've compared the forces. Now it wants me to write an equation, B. Adam, what's my equation? More specific. And you might want to lift your head off the desk. That's why I went to you. Thank you. You're still with me? I was a little worried there. Adam, what does part C want me to find? Okay, as far as I'm concerned, I can either give you air resistance and say find acceleration. I can give you acceleration and say find air resistance, or I can give you both, solve for M. We haven't got to that one yet, but that's going to be fair game this year. How would I get the F air by itself, Adam? So what am I going to write? F air equals, what's my new equation? So it's going to be M 90 A 1.5 plus M 90 times 9.8. Can I do that in my head? I could factor out a 90, so it's going to be 10.8. It's going to be 11.3. It's going to be 9 times 11.3. 90 times 11.3 is going to be 990 plus 27. Is it 1017? I called it 1020 for 3 sig figs. I can do the math in my head. So yeah, air resistance can be larger. And then terminal velocity is when air resistance is equal. The force of air resistance, me being technical here, is actually not a constant value. In fact, the force gets larger as speed increases. A falling object will eventually reach the point where the force of air resistance equals the weight, the mg, of an object. At this point, it will hold a steady speed. Who remembers what we call that? We said it a few minutes ago. That's terminal velocity. Looking at the parachutist mentioned above, what would be the force of air resistance once terminal velocity is reached? If A is 0, it would be mg plus 0, right? Or 0 plus mg, whatever. So it's just going to be plain old mg. It would be 90 times 9.8. It's going to be 900, take away 18. So it's going to be 878? No, 882? Or am I wrong? What do you get? Is it 882? Example 10, a parachutist jumps out of a plane and free falls. They reach terminal speed. We're going to call it speed, not velocity, because technically the velocity would be negative because we'd be pointing down all the time. And I want to draw positive values, so I'm just going to talk about the magnitude. They reach terminal speed. They maintain that speed for a while. Then they open their parachute. They quickly reach a different terminal speed, and they descend to the ground. Sketch not a velocity time graph, a speed time graph. This is going to be kind of a rough sketch. On the y-axis, I'm going to put speed, v. And on the x-axis, I'm going to put time, t. And really here, I'm talking about vertical speed. So, before I jumped out of the plane, I was just sitting on the edge getting ready. What's my vertical speed before I jump then? So there would be a stretch of 0 high. It would last a little longer than I've just drawn, but there would be a stretch when my speed was 0. Then I jump. Wah! What happens to my speed when I jump? Bigger, smaller, or stays the same? Bigger. So let's say there's my new speed. Here's my question. How would I connect this? Don't write this down. I don't think it's going to be a straight line because air resistance changes. What's my air resistance right the split second I jump before I start moving? So what's my acceleration right when I jump before I start moving? That's when my speed is increasing at its maximum. But then as air resistance kicks in, my speed is going to increase slower and slower and slower. I think it would look kind of like this. And then there's my leveling off terminal velocity for a while. Really quick change in speed, steeper line, and then doesn't change as fast, doesn't change as fast, doesn't change as fast, levels off. I would be in free fall for about 30 seconds, pull my cord. What happens to my speed now? Okay. Does it go to 0? No. So I'll have a new terminal velocity, let's say right about there. But how would I connect these? I think right when I pull my parachute, air resistance is the largest. Is that okay? So the speed is going to decrease the fastest. I think it's going to look something like this. And then I'll achieve a new terminal velocity. And here's where my graph is not going to be accurate. Once I'd opened my parachute, I was actually up there for about another 5 or 10 minutes. And so this line, don't write this down, should continue all the way that way and off the page, but I can't fit it. So this is going to be the drifting down with the parachute section, but it should be longer. Then eventually I landed on the ground. What was my speed then? I think it would look something like that. Except the scale is wonky. Yeah? If it was vertical, I would have sustained an infinite acceleration and broken my legs. What we did is we skidded in gently. Or if I hadn't skidded in, I would have bent my knees and rolled, which is what they do like in the military. So I don't think it's dead vertical. We try and cushion it and spread out time a little bit. Otherwise, we'd have issues. You figure this out when you're a kid on the playground. When you're 6 or 7 years old and you're jumping off playground apparatus, you learn, I don't land stiff-kneed. I tuck, I bend my knees, and sometimes I even roll, and it doesn't hurt. What you're really doing is you're increasing time, reducing the force. Oh yeah, speaking of free fall, Mr. Duke has the video. First of all, what's your homework? So you can try number 1. Number 2 is good. 3 is good. 4 is good. 5 is good. 6 is good. I'll do 7. I'll skip 8. 9 is good. 10 is good. 11 is good. 12 is good. 13 is good. Skip 14. Also, from the big Ultimate Vector Dynamics assignment, you should be able to do those questions if you want to get a head start.